Hi, I am Professor N.K. Pandey from Department of Physics, University of Lucknow. I have been uploading some of my lectures on the YouTube on various topics in quantum mechanics. And in the sequence, today I am going to discuss on a very important topic that is considered as linking the classical electromagnetism. Now, it is a bridge between the classical electromagnetism and the development of quantum theory. So today I'm going to discuss on Bohr model of hydrogen atom. Now let us first of all start with the postulates of Bohr model. Then, according to this model, the electron revolves in discrete orbits around the nucleus without radiating any energy. Now mind it, it is not radiating any energy despite being accelerated. Any electron, if it is orbiting around the positive nucleus, it is certainly accelerated, and any accelerated charged particle should radiate energy according to classical electromagnetism. But this is not radiating. And why it is not radiating? Because these discrete orbits are stationary orbits. Now, what are these stationary orbits and why in these orbits the electrons are not radiating? That we will deal little later. But right now, let us understand that the postulate of Bohr model is that till the electrons are in these stationary orbits, they will not radiate any energy. Now, there will be no orbit in between these stationary orbits. Other orbits are not allowed. The next postulate of Bohr model is, that is a very, very important postulate, is that the angular momentum of electrons in these orbits is an integral multiple of h cross or reduced Planck's constant. And we can say it that if m is the mass of the electron, v is the velocity of the electron, and r is the radius of the orbit, then angular momentum mvr is equal to nh cross. That is, this angular momentum is an integral multiple of h cross. Now, electron loses energy only when it jumps from one allowed energy level to another allowed energy level. Now, it radiates energy in the form of electromagnetic radiation with a frequency nu determined by the energy difference of the levels according to Planck's relation, and that is E2 minus E1 is equal to h nu. Now, E2 is the energy of the orbit from where the electron is making the jump, and E1 is the energy of the orbit on which the electron is making the jump. So this difference of energy between the two orbits, E2 minus E1, is h nu by Planck's relation. Here, Bohr assumed that during a jump, a discrete or quantum of energy was radiated, h nu. Now, this Bohr explained the quantization of radiation because of the discreteness of atomic energy levels. There was no involvement of quantum theory here. It was only that the orbits were discrete, and therefore only discrete values or quantum of energy could be released. Now, Bohr did not believe in the existence of photons, mind it. According to Maxwell theory, the frequency nu of classical radiation is equal to the rotation frequency nu of electron in its orbit, of course with harmonics as integral multiples of this frequency. This result is obtained from the Bohr model for jumps between energy levels, let us say En and En minus k. Here k is much smaller than n. This difference in the energy levels is much smaller than the principal quantum numbers. Now these jumps reproduce the frequency of the kth harmonic of orbit n. Mind it, for sufficiently large values of n, the two orbits involved in the emission process have nearly the same rotation frequency. And hence, when an electron jumps from one orbit to the other, the radiation frequency almost remains the same. So this gives credence to the classical orbital frequency as to why we get the classical orbital frequency in a jump from one orbit to the other. Now this is for sufficiently large values of n. Of course, when n is small, or the difference in the orbits, that is k, is large, the classical interpretation fails to explain the radiation frequency. There is mismatch. This has led to the birth of the correspondence principle. Quantum theory agrees with classical theory only in the limit of large n. Bohr's model holds good for hydrogen atom. And what is hydrogen atom? Hydrogen atom is the simplest atom with one proton in the nucleus and one electron. The model is also applicable to hydrogen-like atoms. That is, in which there is only one electron revolving, or ions, of course. Helium plus, lithium 2 plus, beryllium 3 plus. Let us consider some of the drawbacks of the Bohr atomic model. Of course, Bohr model had some limitations, and therefore it was replaced later by quantum mechanical model. This model stood strong in explaining spectra of lighter atoms similar to hydrogen, but it could not explain the spectral lines of heavier atoms. Like this model could not account for hyperfine structures like doublets or triplets. Next drawback is, as per the Bohr model, the angular momentum of the electron in the ground state is h cross or h by 2 pi. However, the modern quantum theory says it should be 0. This model did not stand to the advent of dual nature, that is wave-particle duality of the electron. And here is one thing. The famous Heisenberg uncertainty principle. The Bohr model is in contradiction to the Heisenberg uncertainty principle. Because Heisenberg uncertainty principle states that the position and momentum of a particle cannot be determined simultaneously. Whereas Bohr model defined the position, that is the orbits, and the momentum of the electron at the same orbit. So it was contrary to the later development of Heisenberg uncertainty principle. Let us assume a circular orbit for electrons for convenience. Let us say that. So we have this circular orbit. We have the positive nucleus, and the electron is revolving around this in an orbit of radius r. The centripetal force is acting toward the center, and this centripetal force is provided by the electrostatic force of attraction between the positive nucleus and the electron. And this electron at any point of the circle is moving tangent to the circle, as you can see by the red arrow. So we have the centripetal force mv square by r, the force holding the electron in an orbit of radius r from the nucleus, that is centripetal force 1 by 4 pi epsilon 0 e square by r square. So according to the Newton's law, second law of motion, we have mv square by r is equal to 1 by 4 pi epsilon 0 e square by r square. And the electron velocity v from this one, you can see, is related to the orbit radius r by the formula from the above. V is equal to e upon square root 4 pi epsilon 0 mr. Now let us see kinetic energy of electron in the orbit, that is T is equal to half mv square. Potential energy of the system is minus e square by 4 pi epsilon 0 r. So the total energy half mv square minus e square by 4 pi epsilon 0 r, and from the earlier formula for V, if we substitute, the total energy will come out to be minus e square by 8 pi epsilon 0 r. Now you can see the total energy of the atomic electron is negative. Now, if the total energy of the system is negative, it is a bound orbit. If the total energy is positive, it is an unbound orbit, and electron would not be bound to the orbit or to the nucleus. This is certainly a bound orbit we have here. If the energy becomes 0 or positive, the electron is not bound to the nucleus. Experiments show that 13.6 electron volt energy is needed to remove the electron from the hydrogen atom orbit. And R comes out if E is equal to 13.6 for the ground state. If we put, then R, that is the radius of the first Bohr orbit, comes out to be 5.3 into 10 to the power of minus 11 meter, that is 0.53 angstrom. Now let us consider slightly deviate away from Bohr model and consider the wave behavior of electron as per the Broglie matter waves. So the wave behavior of the electron in the Bohr orbit, that is given by the Broglie formula, lambda is equal to h by mv. The electron speed v is given by v is equal to square root 4 pi epsilon 0 mr. there should be a square root over here. As we can see, we have already seen for V is equal to earlier. Yes, here it is V is equal to. So consider here as a square root to be involved herein. So we can see from here that V is this much. So if we put the value of V in the above equation, then lambda comes out to be 33 into 10 to the power of minus 11 meter. Now, let us calculate the circumference of the first Bohr orbit. And incidentally, 2 pi r will also come out to be 33 into 10 to the power of minus 11 meter. And this is not just a coincidence. This indicates to the development of a particular theory. And this also gives credence to the quantization of angular momentum by Bohr. Now, this circumference is same as wavelength. Okay? So we have the orbit of the electron in a hydrogen atom corresponds to one complete electron wave joint on itself. According to the Broglie principle, a matter wave is associated with the electron. That matter wave has a wavelength lambda that we have calculated above. And the 2 pi r, that is the circumference, is also the same as the wavelength. So we can conclude that the orbit of the electron in a hydrogen atom corresponds to one complete electron wave joined on itself. Now, the fact that electron orbit in a hydrogen atom is one electron wavelength in circumference provides the clue needed to construct a theory of the atom, and that was the later day development in quantum theory. Let us use the concept of electron matter wave. The Broglie provided a rationale for quantization of electrons' angular momentum in the hydrogen atom. That is what I pointed out. Now, let us see the physical explanation for the first Bohr quantization condition comes naturally when we assume that an electron in a hydrogen atom behaves not like a particle, but like a wave. Let us imagine a stretched string that is clamped at both ends and vibrates in one of its normal modes. If the length of the string is L, the wavelength of these vibrations cannot be arbitrary. Mind it, not all the wavelengths will fit into that length L. Rather, it must be such that an integer k number of half wavelengths fits exactly on the distance L between the ends. This is the condition for standing wave on a string. If you remember, the frequency of such waves in a string for standing waves is given by n is equal to some number p by 2l square root t upon m. T is the tension in the string and m is the mass per unit length in the string. And we have different number of loops over there on the string fitting into the length of the string, and the numbers will be such that the length will have odd number of lambda by 2. Now, we have here what we have just now proposed. A and B, in between A and B, we have a string and that has a stationary wave vibrating. Now, suppose we bend its length into a circle and fasten its ends to each other. So if we are bending it into a circle, then we will have a picture like this. So A and B coming together are here, and all the 6 loops are fitting onto this one, you can see. And this is what the wavelength lambda is that we have shown over here. So we bend its length into a circle and fasten its ends to each other, then the picture will look like this. Now, this produces a circular string that vibrates in normal modes. Now, this satisfies the same standing wave condition, but here there is a difference. Here, not the odd multiple of half wavelengths will fit, rather an integral multiple of wavelengths is going to fit on the circle. This means that the radii in Bohr model are not arbitrary, but must satisfy the following standing wave condition, and that is 2 pi Rn for the nth orbit is 2n into lambda by 2. So only these radii will be permitted, which will have an integral number of wavelengths fitting onto the circumference of the circle, and these waves are the the Broglie waves of the moving electron or rotating electron on the orbits. Now, if an electron in the nth Bohr orbit moves as a wave, its wavelength from the last formula will be given as lambda is equal to 2 pi Rn by n. The electron wave of this wavelength corresponds to electron's linear momentum, that is P is equal to h by lambda. Put lambda from the above expression. So P is equal to nh by 2 pi Rn, nh by Rn. And that means if you take Rn to the left, then it becomes on the left hand side, we have the angular momentum, that is Rn into P. And so angular momentum Ln is equal to Rn into P is equal to R into nh by Rn, that is nh cross. You can see from here that we have gone from the Broglie wave concept and we have derived the angular momentum postulate of the Bohr model. That is, the angular momentum in nth orbit is an integral multiple of h cross in that orbit. Now, this equation, of course, is the first of Bohr's quantization conditions. This provides physical explanation for Bohr's quantization condition, and it is a convincing theoretical argument for the existence of the Broglie waves. Now, if n is equal to 2, we have 2 waves fitting onto the circumference. If n is equal to 3, we have 3 waves fitting onto the circumference. If n is equal to 4, we have 4 such waves fitting onto the circumference as per fitting into the Bohr model, and giving a clue from the Broglie wavelength into proving the quantization of the angular momentum in the case of Bohr model. Now, why are these only vibrations possible in a loop? Now, we can see from this one, if it is not an integral multiple of the wavelengths, then naturally we will have a destructive interference. If a fractional number of wavelengths is placed around the loop, destructive interference will occur as the waves travel around the loop, and the vibrations will die out rapidly, and it will not give us a stable atom. By considering the behavior of electron waves in the hydrogen atom, and as analogous to the vibration of a wire loop, we may postulate that an electron can circle in a nucleus indefinitely without radiating energy, provided that the orbit contains an integral number of the Broglie wavelengths. And mind it, this is what we mean by the stationary orbits as proposed by Bohr. That only in these orbits the electrons will not radiate. Only in those cases where an integral number of wavelengths fit onto the circumference of the orbit, those orbits will be stationary orbits, and when the electrons are there in those orbits, the electrons will not radiate. Now, this postulate combines both the particle, as the electron as a particle is moving on the orbit, and wave characters of an electron into a single statement, because it is only through the wavelength of the Broglie waves of the electrons that we are able to establish the angular momentum quantization as proposed by Bohr. While we can never observe these antithetical characters, that is the waves and the electrons simultaneously, they are inseparable in nature. It is a simple matter to express the condition that an electron orbit contains an integral number of the Broglie wavelengths. The circumference of the circular orbit of radius r is 2 pi r. So we may write the condition for stability as 2 pi Rn is equal to n lambda, n is equal to 1 to 3 as final condition. So the radii, permitted radii, by that one will be n square h square epsilon 0 by pi m e square, n is equal to 1 to 3, etc. So these are the only radii permitted as we have come through the Broglie concept. Now, energy in the nth orbit is given by minus e square by 8 pi epsilon 0 r. Now, substitute for Rn from the last formula, we will get En is equal to minus m e power 4 by 8 epsilon 0 square h square by 1 by n square. Now, n is equal to 1, 2, 3, 4, etc. Now, energy just specified by these equations are called energy levels of hydrogen atom. The levels are all negative, signifying that the electron does not have enough energy to escape from the atom. The energy level E1 is called the ground state, and E2, E3, E4, etc. are called the excited states. As the quantum numbers increase, the corresponding energy En increases and approaches 0 in the limit of n tending to infinity. For n is equal to infinity, En is equal to 0, and in that case, the electron is no longer bound to the nucleus to form the atom. Now, the ground state energy, E1 of the hydrogen atom, is a convenient energy unit for use in various aspects of atomic and molecular physics. This energy is called the Rydberg, and its numerical value is what we had seen outside the bracket, that is 1 Rydberg is equal to me power 4 by 8 epsilon 0 square h square, and this comes out to be 2.17 into 10 to the power of minus 18 joule, or 13.6 electron volt. And here, this is how we can plot on a vertical scale the energy of electron in various orbits of the hydrogen atom. The ground state is minus 13.6 electron volt. In the second one, it is minus 3.4 electron volt. In the third one, minus 1.51 electron volt, and so on. And for n is equal to infinity, E becomes 0, and for this, the electron becomes free electrons. So this one, n is equal to 0, is the ground state, and this all are the excited states. So this is a vertical scale on which the energy of the hydrogen atom in different orbits has been plotted. When an electron in an excited state drops to a lower state, the lost energy is emitted as a single photon of light that we know. According to the model, an electron cannot reside in an atom except in certain specified orbits. The quantum number of the initial state, higher energy level, is Ni, and that of the final state, lower energy level, let us consider it as Nf. Then we can say initial energy minus final energy is equal to photon energy, even Ei minus Ef is equal to h nu. Initial energy Ei is equal to minus me power 4 by 8 epsilon 0 square h square by 1 by Ni square. Similarly, final energy Ef is equal to minus me square by 8 epsilon 0 square h square 1 by f. Nf square, energy difference between these two states, that is Ei, that is from where the electron is making a jump. Ef, or the orbit on which the electron is making a jump, is the difference of the two, and this comes out to be Ei minus Ef is equal to me square by 8 epsilon 0 square h square 1 by nf square minus m by ni square. Again, nf is the quantum number of the orbit on which the electron is coming, and ni is the quantum number of the orbit from which the electron is making the jump, or the initial state. Now, the frequency of the photon released in the emission is Ei minus Ef by h, and that is one more h will come in the denominator, and h square will become h cube. So nu is equal to this much. Me power 4, 8 epsilon 0 square h cube 1 by nf square minus 1 by ni square. In terms of photon wavelength, if we want, lambda is equal to c upon nu. So we can write down for lambda, 1 by lambda is equal to nu by c, me power 4 8 epsilon 0 square ch cube 1 by nf square minus 1 by ni square. This expression states that the radiation emitted by excited hydrogen atoms should contain certain wavelength solid. Not all wavelengths are possible. That is, Rutherford model had proposed the continuous spectrum, whereas this model is giving discrete values of lambda. That is, only certain values of wavelengths are permitted, not all the wavelengths are permitted. And this is what was observed experimentally also. These wavelengths fall into definite sequences that depend upon the quantum number nf, that is the final one of the final state of the electron. Now, the calculated formula for the first 5 series are nf is equal to 1, that is all the electrons from nth level are jumping on to the final orbit for which quantum number is 1. So nf is equal to 1, and n for other orbits is equal to 2, 3, 4. Then this is the Lyman series. For nf is equal to 2, we have the Balmer series. All the lines forming this series are called the Balmer series. For nf is equal to 3, we have Bastian series. For nf is equal to 4, we have bracket series, and for nf is equal to 5, we have Fund series. So if you want to see it in terms of the energy levels, so we have those energy levels shown over here in different orbits. We can see from here. So all the electrons jumping onto the first level, that is shown by over here, shown by this violet one, to this one, and that is Lyman series, Balmer series, Paschen series, Brackett series, Fermi series. And similarly, if we see it on the vertical scale, then for n is equal to 1, that is the final NF is equal to 1, we have Lyman series. For NF is equal to 2, we have Balmer series. For NF is equal to 3, we have Paschen series. For NF is equal to 4, etc., we have Brackett. For NF is equal to, we have Fermi series. So this is how we can show the jump of electrons from different orbits to the first or second or third, and they all making different series. The 5 series we have shown over here, and then after that the continuum. Now let us review whatever we have seen in a nutshell. What can we say about it? The Bohr model, what did it do? We have this Bohr model was developed to meet problem posed by discrete energy levels. As I have already discussed, Rutherford model was giving an erroneous result that hydrogen atom spectrum could be continuous, whereas experimentally discrete energy levels were there. Experimentally discrete wavelengths were found in the radiation, so discrete energy levels were there. So the Bohr model was developed to meet the problem posed by discrete energy levels and not the continuous spectrum. So this was later attributed to the wave nature of electrons, and this was described, this wave nature of electrons was described in terms of the Broglie hypothesis, and this Broglie hypothesis made use of what? Planck's hypothesis. So we have a sequence going from the Bohr model. So why it was developed? Because of discrete energy, to explain discrete energy levels. That was because of wave nature of electrons. That was explained in terms of the Broglie hypothesis that made use of Planck's hypothesis. Similarly, what did the Bohr model postulate? Angular momentum quantization. What did the Bohr model calculate? It calculated classical electron orbit. It calculated electron energy. It calculated orbit radius. Then we have Bohr model. It had a failure. Why did it fail? Because it could not explain hyperfine structure of the spectrum, of course. It gave definite position and momentum of electrons in the orbits, contrary to the later development of Heisenberg's uncertainty principle that is stated that position and momentum could not be determined simultaneously. Then it could not stand to the dual nature of electron. And of course, according to Bohr model, angular momentum in ground state was h cross, whereas the quantum theory proposed it to be 0. So we have Bohr model gave way to quantum theory, and quantum theory was developed in terms of the Schrodinger equation, and Schrodinger equation gave the solution of the Schrodinger equation resulted in what we call the wave functions. And what were these wave functions? These wave functions contained all the informations about the Broglie wave associated with the particle. And these wave functions were defined as the probability density mod. This wave function that we call the psi, this mod psi square defines the probability density or the probability density of locating a particle at any point xyz in space at the instant of time t. This wave function psi is a complex one. It could be positive, it could be negative, and to give a positive probability, the mod psi square was used, and this wave function became the most important wave function for explanation of most of the phenomenon by the quantum mechanics. So this is what we have in the Bohr model, how it developed, what were its problems, what did it give, and how did and from Bohr model, how did the Schrodinger equation or quantum theory or wave function develop. So we have Edwin Schrodinger's photograph from Austrian physicist and Louis de Broglie, French physicist. The Broglie won Nobel Prize for Physics in 1929 after the wave-like behavior of matter was first experimentally demonstrated in 1927. Originally, the Broglie thought that real wave having a direct physical interpretation was associated with a particle. The wave aspect of matter was formalized by a wave function defined by Schrodinger equation. Wave function is a pure mathematical entity. That is, psi is a pure mathematical entity. It is complex. It could be positive. It could be negative. And it has a probabilistic interpretation. And it doesn't have the support of real physical elements. This wave function gives an appearance of wave behavior to matter without making real physical waves appear. So here is one simple thing for you. A director in his chamber is waiting for a package. The package comes, and the postman says, please confirm here that you have received the wave packet. Now, this is a wave packet of the Broglie wave. This is not the packet, this is the wave packet. Thank you very much for your kind attention.